Hello everyone. Um, Today I'm going to talk about prime numbers, and essentially I want to talk about two aspects of it. First is what really are prime numbers, and second is a theorem which says that there are infinitely many primes. So these are the topics that we'll be going to cover today. Okay. So the definition of prime numbers is that natural numbers greater than 1 having only two factors, and the factors would be 1 and the number itself are prime numbers. So this is the definition of prime numbers. So uh, all the natural numbers are 1, 2, 3, 4, 5, 6, and up till infinity, right? So how would we identify prime numbers? It's on the basis of this definition. Of course, your 1 is not a prime number because you are saying natural numbers greater than 1. Next is 2. 2 has two factors, 1 and 2, so it would be a prime. 3 has two factors again, 1 and 3, so it will also be a prime. 4 has three factors, 1, 2, and 4, so not a prime. Again, 5 has 1 and 5 as factors. 6 has 1, 2, 3, and 6, so again not a prime because it has more than 2. So, based on this definition, initial few prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, and so on, right? So this is basically the definition of prime numbers. One thing that people generally forget is that, and we should remember, is that 1 is not a prime number. Okay, so someone could say that 1 has only two factors, 1 and itself, right? But that is not true because from the definition of prime numbers, we are only taking starting from 2 and beyond, right? So yeah, that's the definition of prime numbers. So now coming to the second part, which I want to discuss today. I want to discuss a theorem. It says that there are infinitely many prime numbers. How we can prove that, right? The most famous proof for this is given by Euclidean, although there are many proofs, but the basically the easiest and the most elegant proof was given by Euclidean, which is proof by contradiction, right? So that's what we'll be discussing. Okay. So let's just suppose, okay, that we have finite primes and Pn is the last prime number. Okay, that is our assumption. Okay, so I'll make another n. Okay, so here P1 is basically the first prime number, P2 is the second prime number. So this would be 2 into 3 into 5 and 7 into Pn is our last prime number based on our assumption. And I'll add 1 to this number, what I have just written, and I'll say that this is a number alpha, right? Clear till now? Next, I will say few things and which will help us, improving things. So alpha, first of all, alpha is greater than 1, right? Alpha is also greater than Pn, right? Alpha is greater than 1 because we are adding a positive number to 1, right? Alpha is also greater than Pn, again, because we are multiplying with a positive number. Okay. And the major point in this is that uh, alpha is not divisible by any prime before, right? So what I'm saying is, if you try to divide alpha by any prime, maybe it may, let's say, even if it is P1 or P2 or P3 or even Pn, will always get 1 as remainder, right? Because it is, we are adding, ultimately, we are adding 1 to the number, right? So in any case, if we try to divide alpha by any number, we are getting 1 as remainder. So it is not at all divisible by any prime number before, right? And I am saying that based on this, we can clearly say that alpha doesn't have any factor apart from 1 and itself, right? Now, you could argue that can't there be any number which is not divisible by any prime and still it can't be a prime? So that is not the case. So if you pick any number, let's say 6. So I'm saying that at least there should be one prime number before it which divides it, right? So for example, 2 and 3 are prime numbers which divide it, so it cannot be a prime. Similarly, any number x, if it gets divided by any prime number before it, so it's not a prime. And the opposite thing is also true. If it is x is not a prime, then there must be a prime number before it which completely divides, right? So based on these two things, I can clearly say that alpha is a prime number because it has only two factors, one in itself, right? And alpha is also greater than 1. So it matches with our definition. And also we have established that alpha is greater than Pn. So that means a number exists which is greater than Pn, which is a prime number. And this contradicts our initial assumption that Pn is the last prime number. So this is a proof by contradiction that there cannot be a finite amount of prime numbers. Even if you want to, a last prime, we can anytime generate a prime number greater than. So that's it for this class. I hope you understood something about prime numbers today. So thanks for watching and stay tuned to this channel for more such informative videos. Thanks a lot.